Okay, so to begin with today, we're just simplifying. So I see these when I'm doing the quadratic formula problems, and I get to the end and it looks like this. And if you leave it this way, you'd have it marked wrong because you haven't simplified it all the way. 3 goes into all of these, that, and that. 3 goes in here twice, 3 goes in here once, 3 goes in here once. That's a fairly good way to do it because that way you at least have put ones where they were, because kids sometimes think that they just disappear when they cancel, but they turn into ones. Like this one is going to kind of disappear because dividing by 1 really doesn't do anything, right? So then it's just 2 plus or minus. Do I have to put 1 square root of 5? No, I can just put square root of 5. There it is. But it's like in this kind where kids get in trouble when they think it just disappears because they go, oh, cancel, cancel, it's gone. And the answer is 21 root 3. Well, that's wrong on a couple levels. First of all, this cancels too. 7 goes in here once, 7 goes in here once, 7 goes in here 3 times. And the answer should be 3 root 3 if you were even going to just make one mistake. What's the one mistake I've made now? I left off the 1 at the beginning. See, there's a 1 here. So it's 1 plus or minus 3 root 3, and that's the right answer. Now, could I put that all over 1? Yeah, but that's kind of extra work that doesn't do anything. So, all right, so that's one kind. Here's another kind that you need to be good at. Let's say that it's 3 plus or minus 3 root 25 and make it negative just to make it extra spicy. Write that one down. And I'm doubting anybody in here will have the right answer if I ask you to simplify it. Try it. See if you're smarter than I think you are. Don't say it now, so I'll end up 10 people getting it right because they heard somebody whisper it from the back. See, I heard that. And some of you probably aren't even going to try because you know that I said it was really hard. It's really not that hard. You just have to know something. To know something above what the average student knows. All right, so some of you are like, well, this looks the same as the other ones. 3 goes in here once, 3 goes in here once, 3 goes in here 6 times, so what's the big deal? 1 plus or minus 1 root and a root negative 25 over 6. You think you can go farther than that? Really? Okay, what do you think? So final answer? Oh, you're so close. There you go. A few people had that? All right. Oh, yeah. Everybody had it. Sure you did. Okay. I believe a few of you had that. Okay. So now, let's do one more like that. 14 plus or minus 7 root, what should I make this? 3i. No, not I. 3. I can't be under the root. 3 with a negative all over 21. Now, we'll see who can handle this one. It's not easy. I don't know. Will you? Mr. G. Huh? I wasn't talking to you. I didn't expect you to know it. I thought he might know it. I'm just kidding. Go ahead. Go ahead. Because you said 7 went in here twice. So you got rid of that because 7 went in there once. Go ahead. 7 goes in there 3 times. All right. Well, that's a good start. You want to keep going? Oh, you're close. Good. You're close, but you're forgetting something. Yes, Ms. Blue shirt. I'm trying not to say names on the thing. I do know your name, but go ahead.
2 plus or
Yes. Yes. Why can't you bust this thing out of the square root? Because the other one was like a 25, and then you found the square root of it is 5. This one you can't take out because there is no square root of 3. At least you don't know what it is, so you leave it as a square root of 3. You can break the negative out and make it an I. Okay, so there was the right answer on that one. That was the extra double tricky kind. Okay. Now notice we put the I in front because, like, whenever you write like 6 square root of 7, you put the number in front. You never write this. And it makes sense because it looks like the 6 could be under the root. Maybe it is, maybe it isn't. Much better to go like this. That way it's clear the 6 is not under the root. Same idea with an I. If you put this square root of 3 on an I, it kind of looks like it might be under the root. Better to put it out front. All right? Okay. Next part is about... Now we already talked about that enough. Applications. All right, so this one, we had a nice, neat example of a ball on a graph, but I'm going to, since it's Veterans Day, talk about a projectile. Okay, so if you are out fighting, one of the things you have to be able to do is see. And at night, unless you have enough night vision goggles, which back in the old days didn't even exist, I mean, that would have been a huge advantage for these guys that were fighting at night. Nowadays, they have those for pretty much all the guys that need them. And they had to use flares, though, to be able to see. So basically, you shoot these things up into the air that burn, and they stay up there. They're meant to stay up there for a fairly long time. They don't stay up forever, okay? But they go up there, and they burn really bright, like insanely bright, so that even though they're fairly high up above the battlefield, it lights it up so you can see. And that way, you can see if you're either invading or if you're, trying to keep the guys from invading. You can see what's going on so you can stop them. So they launch a flare up into the air. Obviously, it's eventually going to have its highest point. It doesn't go up forever. Okay, so it gets to its highest point. And eventually, what goes up? Must come down. So eventually, it's going to hit the ground again. So those are obviously important points on your graph, is what's the highest it went, and what's this spot here is where it hit the ground. Now, it's important to know that this is height, and this is not distance. People sometimes think this is how far away it was from where it started. It's not. That's the time. So that means when it gets to here, its time is something I can figure out, but its height is really simple. What's its height at that moment? 0. So if I tell you this spot right here, and I say it's like 0.78, 14.5, then I just told you two things: its height and its time. Which one's which? That's the time, because see, that's the x, and the x goes along here, right? That's the time, and that is the height. So that means that 0.78 seconds after the thing got shot out of the flare gun, the height of the flare was 14.5. Now, in the real world, it would probably be hundreds of feet. They don't just launch them really low because they wouldn't last very long. They'd hit the ground really quick. So they launch them super high up there, and they're super bright. Yes? That's a good question. In this case, it's important to understand that not all things start at 0. A golf ball, for instance, would start at 0 because it's on the ground, right? And then you hit it and it goes all the way up. But sometimes it's higher up. Why could it be higher up? Because maybe the guy who's shooting the thing is standing with it about shoulder height, and then he shoots it, okay? So it makes sense that it can be off the ground. That's also known as the y-intercept, right? So that is valid, like it happens in the real world. And the person throwing the ball, too. You start with the ball up high, and then you throw it. You don't usually start with the ball on the ground and then throw it. You start with it up here. So it makes sense that you're going to have a starting height. Now that does bring up the point. If you graph one of these on your calculator and you extend it all the way out, you've got this possibility, which is talking about, wait a minute, time is less than 0. That implies negative time. And so we throw those out because it's not real world. But there's something interesting. It just happened this year. First time it's ever happened. Any teacher could ever talk about this. They have measured particles now that are faster than the speed of light. And that really screws up the theory of relativity, because that was Einstein's whole theory was based on the fact that nothing could travel faster than the speed of light. And therefore, that now brings up the possibility of time travel. So if you can have negative time, then it's talking about going back in time, right? So the speed of light, I can't give you the whole chain of why things faster than the speed of light could lead to going back in time, but that was the theory, that if you could go faster than the speed of light, then you could go back in time. In theory, you could take an astronaut, and if you could figure out a propulsion system that would push him in a spaceship at a speed that is faster than the speed of light, he would not age. He would, if you go at the speed of light, he wouldn't age at all. And if you could go faster than the speed of light, he would actually unage. He would get younger and younger. So you could launch an astronaut who's like 50, and he could end up being like 20 by the time he got to his destination. I know, it stretches the brain a little bit. So, yeah, eventually you got to be careful with that, or you're going to have a baby in the capsule, you know. So. Oh yeah, oh yeah. People would definitely buy that. People have been looking for the cure for, you know, like getting old for a long time. So, here's another interesting theory that I'll stretch your mind on this whole topic. If there are unlimited planets out there, they haven't found an edge of the universe yet. The universe seems to be unlimited, as in there are so many planets that we can't count them all. In fact, they think the universe might even be growing, and in fact, some scientists theorize that since we can't find the edges of it, that it is actually infinite. Infinite. Now, just that means that there is not a limit to how many planets. There's not a certain number of planets, that they are unlimited. Now, they don't know, but if there's a very, very large number of planets, and there's only a certain number of ways that planets can be arranged as far as their matter, then there should be a number of Earths out there that are just like our Earth, that are the same distance from their sun, and they have the same makeup of like how much water it has on the planet. Like, we're unusual because 2/3 of our planet is water, right? And they're trying to find other planets that have any water on them. They get a little bit on the moon, and they found some other planets that might have had some water on them. But we have so much water, it's just unusual. What if there's another planet just like ours? And then here's the crazy part, when you start talking about infinity. If there's an infinite number of planets out there, then there's obviously got to be another one like ours. In fact, there's got to be an infinite number of Earths out there if there's an infinite number of planets. And if there's an infinite number of Earths, then shouldn't on one of those Earths there be somebody who's a humanoid that's a lot like you? Because there's only so many ways that matter can be arranged when it comes to human beings. And so, yeah, your mommy told you were special, I know. Just like everyone else. So anyway, if you go to that place where all of a sudden there is an infinite number of planets, therefore there's an infinite number of Earths, and therefore there's an infinite number of you out there, then there's probably some other planet where they're having a math class just like this, with the math teacher just like me, where they're talking about how there's an infinite number of planets and an infinite number. And here's the really weird thing, it might have all happened 1,000 years ago. Okay, anyway, moving on. The key points here. This spot, and this spot. And I'm going to show you how to get those today off of your graphing calculator. It's really, really handy for this. So grab your graphing calculator and type in that equation. If you need to borrow one of mine, it's no problem. Just don't sit there. Come up and borrow one. Mind stretcher. All right. So I did my Veterans Day example with the flare, but now we're back to a ball in the air, and I'm not going to try to change all these to a missile or a whatever. But we have our equation right here. Would you please type that into your calculator? I know you don't have a t, but you have an x, and it works the same, right? So type in negative 16x squared plus 25x plus 5. All right, now, once you get that in there and you hit graph, it's kind of annoying. I'll go back to the way mine was first time too. If I zoom 6, I can't see the top of the stupid thing. So what do? Well, you can go to your window button and say, I want to go up higher. Is higher an X thing or a Y thing? It's a Y thing. So I go to window and I make my Y max, make it like 20. And I hit graph. And now I can see it a lot better. And if I really want to make it nicer, aren't I kind of wasting space on left, right? That's the X's. I really don't need X's to go that far, do I? I could have X's go from like 0 to like 5. So I can go back to my window and I make my X's go from 0 to 5. And I hit graph again. Oh, I can see it even better now. Question? You having trouble getting yours to work? Okay, then have you tried the window thing yet? Okay, then go to Y, hit your Y equals button, and compare it to somebody sitting next to you. And did you use a minus or a negative for the front? All right. All right. Try doing use T. Ah, it could be a problem. Use X. Yes.
By the way, it graph says invalid dim.
All right, that means that your dim is invalid. Oh, let's see that plot on the top? Get that plot turned off.
Oh, okay.
You have a plot on. Okay, so now we've got our little picture of our ball going up in the air. Now, if they ask you, what is the highest that the ball ever went, you know you needed to get that top spot, right? That's called the maximum. Everybody go to second, calculate. It's right above trace. And which one do you think we're going to pick? The maximum. Second, calculate maximum. So it's under this red button right there. See, second, calculate maximum is the 4. So now, this is important to learn because you're going to use this over and over again this year and next year. Okay, so let's get good at this. It says left bound. That means get just to the left of the spot you want. You're going to make boundaries on this. And you want to get just to the left of the spot you want. I got to keep moving until I find my spider. There he is. Okay, I get just to the left of the spot I want. There. Doesn't really matter how far to the left, as long as I'm to the left of it. I hit enter. Now what does it ask me? After you hit enter, what does it say? Right bound. That means I need to get just to the right of it, a right boundary. And now, after I'm just past to the right of it, I hit enter, and it says guess. That means it wants you to go over the top of where you want and kind of get close. And it looks like it's about 0.74 or something, but I'm going to hit enter, and it'll give me the exact. It's actually 0.78, comma, 14.76. Now think about this. This is the top of a parabola. Remember how it gives you two things. It gives you the time and it gives you the height. Which one of these do you think is the time? Yep, that's the time. What's that? So on the graph, the x distance, the x number is the time. That's how much time has elapsed. And the height is how high it is. Okay, so does that make sense? So the answer to this question is, how long was the ball in the air if Joe swings and misses and it hits the ground? Misses it and it hits the ground. All right. I was actually answering how high was the ball, so I shouldn't have been, but we're going to eventually be asking those questions. All right. So if this ball is traveling like it's a pitch, and this is the pitcher throwing it. That was loud. Okay. Then they're asking, when did the ball hit the ground? That's this other spot here. So everybody get back to your graph and your calculator and try to find this spot, right, where it touches the x-axis there. So what's that called? It's under second, calculate. What are those spots called? They're called x-intercepts or the zeros. Exactly. You want to calculate the 0 or 2. Now, it wants me to get to the left of this. Okay, same deal. I know where it is. It's down there by the x-intercept. And I hit enter when I'm to the left of it. I know I'm above it, but I'm also to the left of it. Then you get to the right of it. Arrow over a little farther. Get to the right of it. Hit enter. Get right on top of it. And hit enter one more time. And it should say 1.74. And then it says this weird 1e negative 12. That means 0.00000000000001. If I did my zeros right. That means basically 0. Okay, then you did something wrong. All right, so 1.74, comma 0. The point here is you have to understand, what does that mean? That's the time, that's the height. Doesn't it make sense the height is 0? Because the ball hit the ground. So the height and the time kind of go together, and you got to know which one's which. The x is always the time. Time is always the independent. It's always on the x-axis, so it makes sense. All right, so that number right there is 1.74 seconds. That's how long the ball was in the air before it hit the ground. All right, the highest it ever went, we got that point before. That one was the 0.78, comma 14.7. That meant time, height. At time 0.78, its height was 14.7. What's the only other time that's kind of important? Right here. It's what time is it when it is just about to start but hasn't started yet? Time 0. And what is its height right there? Well, that's kind of important to know. Let's go back to our graph and find it. That's that spot. It's the y-intercept. Now, wait a minute. The y-intercept, that's actually easier to find on the original problem. Because if I look at the original problem here, I got the y-intercept right here. Right? Okay. So now last thing. As you're plowing through this calculator stuff, you have to be able to find 4 important points. One is the beginning. That's the y-intercept. You can find that by just looking at the equation. This one you can find using maximum. This one you can find using 0 on your calculator. And then the other thing is, you can figure out where that ball is at any time. Like if I say after 1 second, how high is the ball? And let me show you how you do that. Everybody pull your graph up. You got the graph up? This is how to show you where to find 1 second on the graph. Go to second, calculate again, and it's not the 0, and it's not the maximum. It is value. You're calculating a value. Hit enter on the 1. Now, see how it says x equals on your screen? That's asking you for an x. That's our time, right? So if we say x equals 1, we're saying time equals 1 second. So hit a 1 there. And after 1 second, where is the ball? See that little spider comes back and shows you that's where the ball is at 1 second. And therefore, its height was what? 14. See how cool that is? So if they ask you for where is it after 1.5 seconds, everybody figure out after 1.5 seconds, how high up is the ball? Second, calculate a value. 1.5, graph it. I hit graph, that was dumb. Second, calculate value of 1.5. Enter. There it is, 6.5. So it's 6.5 feet off the ground. So what we're doing with this one is telling it a time, and it's telling us at that time it was this height. All right, I have taught you a lot about quadratics right there. And these problems are going to come up on your MCA tests, your SAT tests, your next test that you have in this class. So this comes up a lot. So you need to get comfortable with this calculator part. It was all under second, calculate. And the value was the one that tells us we can put in an x number. The 0 is where it touches. The x-intercepts are also known as the zeros. Minimums are low spots in the graph. Maximums are high spots. Intersect is where two lines are intersecting. So this is probably the most powerful menu on the calculator for graphs because it answers so many of the big questions that you'll have on SATs, ACTs, etc. Okay? So you've learned some good stuff here today. All right. I want to actually do one of your homework problems with you here. So instead of doing this last one off the slide, I'm going to grab your worksheet and do the first one with you off of that, or the first hard one with you. So here's your worksheet. 2, 3, 4, 5. I know it's still recording. I think they might want to know how to do the first couple on the worksheet too. 3, 4, 5. That's right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. The very first one is super simple. What is it? 4i, because it's the square root of negative 16, and that's just square root of 16 times the square root of negative 1, which means 4i. It's important that you know how that happened. All right, part B, negative square root of 144. Has this got an I in it? No, because the negative isn't under the root. So you just do it one piece at a time. What's the square root of 144? So it's just negative 12. A lot of them stuck together today. I was afraid of that. Okay. Moving on to one of our review kind of questions here. Number 2A. 2A. Because I think the top ones are going to be pretty easy for you. Oh, wait. There's one thing before we get to 2A that's kind of important. If you know I is the square root of negative 1, right? What's I squared? Wait a minute. I squared, isn't I squared just I times I? Right? Isn't that what I squared means? So then square root of negative 1 times square root of negative 1. Do you guys know that little rule that when you multiply two square roots that are exactly the same, that the answer is what's underneath the root? You are right. It's negative 1. All right. Let's say then, how about I cubed? Isn't I cubed the same as I times I times I? And I already just figured out what I times I was. What was that? That was negative 1. And then I have an I left. So it's negative 1 times I, which would be negative I. How about I to the 4th? Well, that's I times I times I times I. And so this one's negative 1. That one's negative 1. It's negative 1 times negative 1. Positive 1. They keep getting different answers. You'd think there'd be a pattern. I to the 5th. Anyway, some of you that are kind of smart and like patterns, try to figure it out a few ways. It's kind of cool how it just keeps changing. All right, moving on back to your homework here. We were going to do 2A. Y equals x squared plus 2x minus 15. All right. Those directions say solve it by factoring or using the quadratic formula. I'll tell you, if it factors, it's way easier. So let's see if we can factor this puppy. If we can, it's a lot easier than the quadratic formula. So 15. How do I make a 15? 5 times 3, and that has a difference of 2. It seems like a decent chance this is going to work. X and 5 and 3. And the bigger one needs to be positive so that I'll have a leftover of this. So let me just check and see if that's right. Outside and inside have a difference of 2x. It looks like it worked. Sweet. So what's the answer? Negative 5. X equals negative 5. And x equals positive 3. And if you really feel like you got, a bad deal because you didn't get to do the quadratic formula, don't worry. You'll get to use the quadratic formula on the next one. Because I don't think that one does factor. The program is okay, but you have to make the skeleton and put the numbers in. Know what I mean? Negative plus or minus square root of that minus that. Actually, that's a 4. All over to that. I know that that seems like extra work, but we do require, the whole math department requires that you show your work. So allowing you to use the calculator to do it is fine, but you got to show what you put into the calculator. All right, anyway. And there aren't even any applications on this worksheet, but there are on the other worksheet. So I am done with my recording for now.